Chapter 1 Fundamentals of Thermodynamics, Section 1.6 Pure Gases, Liquids, and Solids. So, first, let's talk about gases. What's the difference between a real gas and an ideal gas? Actually, there are three differences. In an ideal gas, the atoms or molecules do not attract or repel each other. The size of individual gas particles is zero. All collisions between the ideal gas particles are elastic collisions. That means the total kinetic energy is conserved. But in a real gas, the atoms or molecules do attract and repel each other at the same time. The size of individual atoms or molecules is non-zero. For example, if we are looking at a helium atom, we can use its van der Waals radius to calculate the size of one helium atom. Also, we can estimate the size of one water molecule. This is pretty easy. As long as we know the density of water, we can compute the volume, the molar volume of ice. And then we use that molar volume of ice divided by the Avogadro constant. We get a rough estimate of the size of a water molecule. Number 3, the collisions between real gas particles are non-elastic. That means the total kinetic energy is not conserved. It might be transformed into potential energy or some other particles. Real gases can be condensed into a liquid or solid due to the attraction between those gas particles. Ideal gases cannot be liquefied because there is just no attraction between ideal gas particles. Over here we have a diagram of a gas, a liquid, and a solid. Over here it can be any diatomic molecule, but let's say this is a nitrogen 2 molecule. So we have a nitrogen gas. Under low enough temperature, we can make liquid nitrogen like this, and if we slowly lower the temperature for the liquid nitrogen, it can become a solid. This is nitrogen solid with a perfect crystalline structure. Now, what are the differences between the gas phase, liquid phase, and solid phase of a substance? So we look at these properties: the shape, volume, density, molar volume, net, intermolecular attraction, and kinetic energy. The first three entries are pretty simple. Molar volume, that's just the volume of the substance per mole. Usually, the molar volume of a gas is approximately 1,000 times larger than the molar volume of a liquid or solid, but it does depend on the temperature and pressure of the gas. At room temperature, 1 bar pressure, the molar volume of water vapor is about 1,000 or 2,000 times the molar volume of ice or liquid water. Now let's look at this intermolecular attraction. The attraction between atoms and molecules is usually strong in the solid phase and in the liquid phase, but it can be really weak in the gas phase. It's just because atoms and molecules are usually only 1 or 2 angstroms away from each other, but in the gas phase, the distance between two gas particles can be 10 angstroms or even longer. With a very long distance, gas particles, well, they still attract or repel each other, but the attraction and repulsion can be really small. Now, kinetic energy. Well, atoms and molecules do move even in the solid phase, but the motion is slow, the speed is slow, therefore they have smaller kinetic energy. In the liquid phase, well, they can move a little bit faster. In the gas phase, they usually move a lot faster than in the solid or liquid phases. For example, at room temperature, oxygen molecules, nitrogen molecules, they typically move at a speed of several hundred meters per second. Now let's look at one example: ice, liquid water, and water vapor. And if you look at the density of ice and liquid water are very close to each other. It's about 1 gram per milliliter. But if you look at the density of water vapor at room temperature, assuming 1 bar pressure, it's only about 0.7 milligrams per milliliter. It's a very small number. Again, this is 1,000 times smaller than this number or this number. Now let's look at the attraction between water molecules in the solid phase and liquid phase. They are about 40 kilojoule per mole. I put a negative sign here to emphasize its attraction. Usually we use a negative sign for attraction and a positive sign for repulsion. And this is net attraction, so that means it's attraction minus repulsion. Now let's look at the water vapor. The attraction is really small. It's only negative 0.04 kilojoule per mole under standard conditions.